Today, I want to tell you about the benefits of equipping your reverse osmosis with a VSD pump. That's a variable speed drive pump. This is a very important topic, seeing how the electricity prices are developing right now. And this is something that's very important to us for sustainability reasons, but also it gives a lot of advantages to the clients. And that's what I want to tell you about today. We'll start with why is energy efficiency important. Then we'll have a look at the operating mode of a reverse osmosis with a variable speed drive pump compared to, let's say, a normal unit with a non-regulated pump and a throttle valve. Then we'll have a look at what does influence the energy consumption of an RO unit. So what effect do the operating conditions have on the energy consumption, and how can we save energy and reduce energy consumption? Then we'll get to the most important part. How can I calculate the savings with a variable speed drive pump? Because that's why we want to equip most of our units only with variable speed drive pumps, because it makes a lot of sense for the client. The saving time over the lifetime of the plant, the savings are really impressive. And we'll show you how to calculate the payback period and the savings yourself with our Excel tool. And finally, we'll just have a recap about how do I convince my client of the advantages? What are all the advantages of having a system with a variable speed drive? So we'll jump right in. We'll start with a, I think, very interesting picture, really. If you had a car, would you drive it at full speed, at full throttle all the time? And when you want to slow down, you press on the brakes? I think nobody would do that. It's just really, really inefficient. But that's what we're doing with the reverse osmosis with a throttle valve. We're basically letting the pump run at full speed all the time, because if it's an unregulated pump, there's only full speed. And we throttle the unit to get to our operation point, to the velocity, let's say, in terms of a car that we want to have. We do that with the reverse osmosis because sometimes we don't think about what it implies. But actually, if you see this example with a car, you realize that a variable speed drive makes a lot of sense for a reverse osmosis unit. We have changed a lot of our units for this year, in our catalog this year, to variable speed drive, or FU in German, only. So we don't offer the versions without a variable speed drive anymore. One of the reasons is we are convinced that sustainability is a really important topic, and our reverse osmosis units have a lifetime of 15, 20 years easily. So how much energy they consume now and in 20 years, that's a very important topic for the environment. And we want to give you a solution that is technologically, that makes sense, that is really advanced. But for us, it's also important that this is a real advantage for you and for your clients. Because energy efficiency is sustainability on one hand. It's an environmental protection measure, but it's also a cost reduction that your client is going to notice right now. So if you replace an RO unit that has been installed, that has a unregulated pump, with a RO unit with a variable speed drive pump, the client will notice the savings, and very large savings, 30–50% or even more, immediately. So this is something that ensures the development of your client, cost reduction of your client, and that might make him come back to you for the next unit. Okay, let's have a look at the development of electricity cost. This is the data for Germany. So yes, Germany has a pretty high electricity cost worldwide and in the European Union. But we'll see that there's a similar development for other countries. Here you can see the cost has been relatively stable. This is for industrial consumers, okay? Household consumers in Germany pay rather like 35 cents per kilowatt hour. So this industrial, but it went up a lot due to the political, economical situation in the last year. And still in 2023, it is not quite so dynamic anymore, but it's still a really, really high value, 40 cents per kilowatt hour. That's quite a lot. This is for any customer, industrial customer, who is looking for a new contract. Old contracts might have lower values, but the companies are trying to go up with those also a lot. We have just tried to show you an example for the new contracts to make a new electrical contract online for our location here in Freiberg am Neckar. And this is for commercial users, so users that don't have a very high electricity consumption, okay? And you see here that you have actually even 69 cents per kilowatt hour. That's really a lot. Or this is industrial consumers. This is lower because industrial consumers get a lower energy price, but you still see this is 20 cents per kilowatt hour. The prices are given only for 1 hour, and then they recalculate. So you see there's still a lot of volatility in the market. And these 20 cents per kilowatt hour are without several taxes, additional charges, and so on. So actually it's around 25. So where we are right now for most of our customers is maybe around 25 to 50, let's say, cents per kilowatt hour. But even if your customers have a lower value, you will see with our calculator that it's still worthwhile to have a variable speed drive. The important thing for you is it's good to ask the customer about this, because normally it's something that is not in focus when you do an investment. Here you see electricity prices throughout Europe. You can see that they vary quite a lot. Greece has an incredibly high value as well. The EU average is somewhere here around 20 cents. And we have calculated a few of the examples also with around 20 cents. So you can check that out. Okay, so this is electricity cost. But no matter what the electricity cost is, what is important when you discuss with a client in the beginning is to think about investment cost and operation cost. And I know it's something that is not so present for all of us all the time, but it's something that's really worthwhile to look at. We have here calculated an example with real numbers. Okay, this is a standard reverse osmosis unit of 10 cubic meters per hour. I have here the operation time that we considered, the yield, and so on, an electricity cost of 0.25 euros per kilowatt hour, and a lifespan of 20 years. These are real numbers. This is the cost for the reverse osmosis unit, and this is the cost for the electricity over the course of 15 years. We have, of course, also water cost, which is considerable, but to simplify matters a bit, we have included only electricity cost here. In the later examples for the calculation tool, I will show you the water cost as well. You see here an example. This was the standard unit. This is the unit with a variable speed drive pump. And you see that there's a small increase in investment, but there's a huge decrease in operation cost. You see here, it's about 6% additional investment that corresponds to 2,500 euros. And your savings in electricity over the lifetime of the unit are 115,000 euros. So that's a big difference. And I'm always surprised when we see units of this size, like 10 cubic meters per hour or larger ones, are still being ordered without a variable speed drive. I know it's something that you might have to convince the client about in the beginning, because many people don't have this on their mind when they invest. But I think it's something that is really worthwhile for the client, and that's going to help you to have repeat business with that client as well. Okay, but let's go into the technical part. So how does a RO with a variable speed drive actually work? So this is a standard reverse osmosis unit. You see there's a pump without variable speed drive, and you see the throttle valve here after the pump. When you start it up, normally the throttle valve is, let's say, 3/4 open, half closed, something like that. Then you see how your flow rates are doing, permeate and concentrate, and you close the valve slowly, incrementally, until you reach exactly the flow rate at the design point you want to have. If you have a pump with a variable speed drive, which is this one here, then it looks a bit different. So you see you have the pump here, you have a variable speed drive that is piggybacking on the pump, so to say. The variable speed drive can also be added to the switchboard. That's possible. It's more useful for larger pumps because this works until a certain size. But with the units that we sell in the flow rates where we are normally moving up to, let's say, 50 cubic meters per hour, this is a very good solution because the variable speed drive is exactly the one that fits the pump. And you see here, you don't have a throttle valve anymore. So what happens here at the startup is that the flow rate after the pump is measured automatically by the unit. This gives a 4 to 20 milliampere signal to the switchboard, and the switchboard adjusts the variable speed drive so that the pump is running exactly at the speed percentage that corresponds to the proper flow rate. So the advantage is also that you don't have to set anything, you don't have to adjust. It is automatically running at the right point. It also runs at the right point if operating conditions change. There's no need to readjust later. Okay, before we look at all the calculations of prices, we have to just look shortly, very shortly, at the technical part of power consumption. So we have several power ratings of the pump. We have P1, which is the power that's received from the electrical grid. This is what the pump is pulling from the grid. This is relevant for our energy consumption because that's really what gets consumed. And this is including all the losses of all the pump components. So we have here first, if we have a variable speed drive, we have losses of the variable speed drive because it's an electrical component. It does have a certain loss. We have losses of the motor, and later we will have losses of the pump itself, the hydraulic part. Now, the losses of the variable speed drive are usually the lowest. They're quite minor, lower than 5%, usually a lot lower than 5%. The losses of the motor are a bit more noticeable. That depends, 7 to 20% approximately. And then we have the losses of the pump. So after these two losses, we have the power output from the motor, or also called shaft power. This is P2. And this goes into the pump, and then the pump produces a certain hydraulic power. What the pump needs to produce, the hydraulic power, depends on the flow rate, which is Q here, the geodetic height, or the height of the pump, that's designated as H, and density of the water, which is usually constant, and G. We have here a certain loss for the pump. This is usually the highest of the losses. That's about 20 to 30%. Depends a bit on which point of the pump curve we are operating as well. We'll come to the pump curve on the next slide. What's important for you to remember is P1 is the relevant power rating that we use for energy consumption calculations. And this includes all the losses, also the losses of the variable speed drive. So, pump curve. I'm sure you all have worked with this before. The pump performance curve, or the QH curve, describes what head the pump reaches, or what height it can produce at a certain flow rate. The blue line here is the pump curve, so the pump always has to run on this curve. In this case, it's an unregulated pump, okay? So it can just run on this curve. And if I have a certain flow rate, if I set the pump to a certain flow rate, I will reach a certain pump head, okay? The red part is the system curve. The system curve basically says the more flow I push through the system, my RO unit in this case, the more pressure or pump head I need to actually get through, of course, because the resistance increases. So the pump curve would start from 0 and go up. And where the two curves intersect, that's the operation point, our yellow dot here. If I work with pump curves, I will have a look at my flow rate that I need for my RO. I will choose a pump that gives me the required head at this flow rate. And I can also read off efficiency and power consumption at this operation point from the sheets of the pump manufacturer. Now, if I use a RO unit with a throttle valve, the system looks like this. I have the pump, I have a valve, and I have the system, the RO unit. Now, let's assume my original operation was the gray line, okay? So let's say this is a 10 cubic meter per hour unit. Let's say Q1 is 10 cubic meters per hour, and I need approximately 12 bars. Okay, this is my design point. Now, maybe the water is warmer, so I need less pressure. Maybe there's less TDS than we thought. The design point gets moved. So what happens if I just start up the unit and I need less pressure, the pump will move on the pump curve, and suddenly it will give me, let's say, 15 cubic meters per hour with 9 bar, because I need just 9 bar to really push the water over the RO unit. But I don't want the 15 cubic meters per hour, because my operation point for the membranes is 12 cubic meters per hour. And it's not good for the membranes to have a higher flux than what we're supposed to have. It's going to affect the lifetime. It's going to affect fouling and scaling. It's not a good idea. So I need to move back to my operation point. If I have a throttle valve, there's only one way to do that. So I will close the valve slowly, and this is the pressure loss the valve produces, the dark blue line, when it is closed, okay? Or half closed or whatever. So what happens is that my red line, this is my system pressure loss, this is lower than at the design point, will be superimposed with a pressure loss from the throttle valve. So I add basically to the pressure I need in the system, which is less than my design pressure, I add the throttle valve pressure loss to reach again the design pressure. Problem solved, you can say. So I'm at the operation point, that's true, but I'm using this pressure or this component of the total power consumption. This is what I need actually for the system. And this pressure part from the throttle valve, this is power that I actually waste. And in a lot of systems, this can be half of the total power if the operating conditions are like that. We'll come to that in the next few slides. So the advantage of this sort of solution with the throttle valve is, yes, it's low investment cost. You can adjust during operation. It's a simple system really, but you have a markedly higher consumption than with a variable speed drive. And also the throttling valve has to be adjusted manually. This is just a line for a certain position of the throttling valve. If the water gets colder again, if the TDS increases, then we have a different power pressure loss of the system, and we need to adjust our throttling valve. And if the RO unit is situated somewhere where nobody ever passes by, let's say the operator knows the plant is running, that's it, no problem. Maybe he will go and check only every 2 weeks, let's say, and then maybe the pump is already running at a point where it really shouldn't run, which is not good for the membranes and for the lifetime and for the replacing of components. So what's the alternative? If you have a pump with a variable speed drive, this looks a little bit different, okay? What we have here is, we have again a pump curve, but we have not one pump curve, we have basically unlimited number of pump curves. Let's assume this pump curve is the one of 100%. So the variable speed drive is running at full speed. Let's assume this one is maybe 60%, for example, or could be 70. What happens now? We have here the system curve as well. Let's say this is our design point, okay? We have here just as well 10 cubic meters per hour as before. We calculated that the unit will need 12 bar. We'll have 12 bar here. Now we have again warmer water or lower TDS. So actually we could be here. We just need 10 cubic meters, but with, let's say, 9 bars, okay? Instead of closing a throttle valve and going up again to the 12 bars, what we do here is this. We have here an unlimited number of pump curves, really. So this pump curve for 100%. Here would be the pump curve for 90%. Here would be the pump curve for 80%. Here is the one of 70. Now, if the one of 80% intersects here, this is our solution. So with 80%, we'll get the flow rate that we need, 10 cubic meters, and we get exactly the pressure that we need, which is 9 bar. So what we do here is we just adjust the speed drive percentage-wise downwards until we reach exactly the pressure that we need. And this is the great advantage of the system, that you use only the pressure you need. You don't have to use anything additional. So you have a reduced energy consumption. It's in practically all cases 30%, and depending on the operation conditions, it can be easily 50%, and for some units even quite a bit more. What you saw in my example of the 65%, so that is perfectly possible, and I'll show you how. We have not only a reduced energy consumption, we also have less noise emissions. It's a more silent unit. This is important if you have people working in the same room. And we protect the unit because we have a soft startup with a variable speed drive. The pump doesn't start up at 100% like one without the frequency control. It starts up low and then ramps up slowly. So we don't have pressure hammers. We have a longer lifespan of the membranes of other units, less maintenance, and so on. We also can use the pump in the 50 and 60 Hz electrical grid as well. Advantage for you is we can warrant shorter delivery times if we use a variable speed drive pump normally for this for 60 Hz, let's say, because we just have a standard pump. We don't need one with a special motor. We have also an excellent matching of components if we have an integrated variable speed drive on the pump, what you've seen in the picture before. There are disadvantages, okay, as with everything. So we have a slightly higher investment because of the variable speed drive. We have typically for our units, it's an additional cost of between 2,000 to 3,000 euros per unit, depending on the size. We'll come to that later in the calculation. And we have small power losses because the variable speed drive has a power consumption too. But I'll show you later that even taking into account the losses and the higher investment, you can recover the money so quickly, the additional investment, that it makes a lot of sense to go for this solution. Okay, before we start calculating, I want to show you quickly what is the energy consumption influenced by, which parameters influence it, and when can we really reduce energy consumption a lot with a variable speed drive. We'll have a look at a standard RO configuration, okay? We have a high pressure pump, we have the RO module, permeate, concentrate, we have a certain concentrate recirculation flow possibly. Maybe we have a dosing pump here. So basically the consumer that is here is the high pressure pump. That's clear. If we have dosing pumps, if you have maybe some motor ball valves, the consumption is really low compared to the high pressure pump. What I want to stress before we go to energy consumption, the connected load of the pump rating, that's what you see in our catalog as well. That's not the consumption. So that's just the connected load. It's usually higher than the consumption, not always, but usually. And this doesn't say in the first place whether two units consume more or less. So if you have one unit with a 1.5, let's say you have one unit with a non-regulated 1.5 kilowatt pump, and you have one unit with a regulated, so VSD, 2.2 kilowatt pump, it doesn't follow that the VSD unit with a 2.2 kilowatt pump will use more. It might use consistently less than the 1.5 kilowatt. Sometimes VSD pumps have a higher power rating than the normal pumps for the same flow rate, but their consumption will still be lower because you can adjust. Okay, now the energy consumption, or what you need as power of the pump, we have seen that before, that depends on the flow rate and it depends on the pressure. For our systems, the RO systems, the flow rate is a given. The flow rate is what you have already decided here for the permeate, what you need, plus concentrate recirculation. Okay, so the inlet and the concentrate recirculation gives you your flow rate. The recirculation is also fixed for process units, so it depends on the overflow rate you need for the module. So basically, you cannot really play around with the flow rate. Okay, so the energy consumption they have is really proportional to the pressure. You can play around with the pressure, or the pressure will vary depending on operating conditions, to be precise. What influences pressure? First, maybe in many cases, most important factor, the total dissolved solids in the inflow. This determines osmotic pressure and therefore determines the pressure you need to work against osmotic pressure, to have a reverse osmosis, and to push the water over the membrane. If you have a high TDS, you will need more pressure. If you have a lower one, you will need less. There's another important factor, temperature. With a higher temperature, you will have more water flow. The water passes the membrane more easily. You also have more, let's say, less salt resistance of the membrane, so that you get a slightly worse quality of the permeate. But what's important for us here is higher temperature will lead to a lower pressure that you need to cross the membrane. Finally, you have inlet pressure. That is something that we often forget. Normally for our units, we require the inlet pressure to be 2 bars in order to have some sort of starting pressure so that the water reaches the pump. In your drinking water network, where the units are often connected, you usually have a higher pressure than 2 bars. So depending on conditions in the factory of your plant, you might have 2, 3, 4 bars. This is a water pressure that is there and that you can actually use if you can adjust the second pump. Now we have also membrane type and membrane aging. Membrane type, it depends a bit on, let's say, the density of the membrane. You can imagine it's either a very tight one, which holds back salt very well. Let's say, for example, a high rejection membrane. But that means also that water is not going to pass there so easily, so you need a higher pressure. Or you have maybe a standard RO membrane that needs a bit less pressure than the high rejection, or you have possibly a nanofiltration membrane, which needs even less pressure. Membrane type is sort of fixed because you want to have a certain result for the removal of the solids, removal of the dissolved solids. So you cannot really play around in the sense that you can choose whatever you want, but you might change the membrane type and then your pump should maybe be able to adjust, okay? What you always have to take into account is also membrane aging. As the membrane is, let's say, ages over the time, it is partially blocked. So some of the pores of the membrane are blocked, and that leads to higher pressure being required to achieve the same flow rate. This is something that has to be taken into account always. Now, what can we do? So one solution we have been proposing is variable speed drive. Now I could also say, yeah, that's great, but I can also adjust the design, right? So I can adjust so that my pump works exactly at the operation point I want. Then I don't need to vary anything. Theoretically, that is possible. So you could adjust for the TDS if you know the values beforehand. If you have a complete water analysis, you can adjust and you can choose exactly the pump you want. You could also adjust for the membrane type. You have a certain design, you know what pressure the membrane needs. Okay, I'll take that one. And you can adjust, if you know it, for the inlet pressure and for the temperature. In practice, there are a few problems with this. So we can have a really extensive adjustment in all details. For large units, it makes sense there. So if you have a 200 cubic meter per hour unit, yes, it makes sense to adjust exactly to the water analysis and everything. If you have a 2 cubic meter per hour unit, or 20 even, it does not necessarily make sense to do that. Because if you adjust everything, you will have for each unit a different pump. So in our case, that means we would have to, we need a longer delivery time for you, because each time we choose a different pump, the one that's exactly fitting. We need all the information from you about the water, which is not always there. And the units would be a lot more expensive because we have to do the design every time from scratch. So for the volumes where we are usually, that we're talking about, up to 50 cubic meters per hour, let's say, it makes a lot of sense to have standardized units and not to adjust exactly to the operation point. But there's also another point. Water quality temperature can vary. If you have no, let's say, security margin at all, then that also doesn't make sense for the operation. You also don't know everything beforehand. And as I said, could change. We need a certain safety margin anyway for membrane aging, and we need that also for temperature variations. You cannot guarantee that they're always the same. So if we look at this, there's always a safety margin required. We will never be able to really use the pump 100% with a fixed speed pump. So it makes sense to use something else. When we are operating, as we said, if we throttle the pump, that's the solution for a lot of the units we see out there, but it's not a good solution. We have a pressure increase to make the pump run on the pump curve, and that means we'll have the maximum energy consumption possible under the operating conditions. If, on the other hand, we use a variable speed drive pump, we adjust here, so we have a certain flow rate, and we adjust the pressure. You see here, let's say we go down to 80%, or here we go down to 60%, and we adjust it until we reach the operation point, okay? We have also an extension of the lifespan of the unit and no manual readjustment. So this is, just to recap, This is technically how throttling valves and the variable speed drive work. I want to show you which units of our RO range we have changed this year to variable speed drive only. And then after that, we'll jump directly into the important topic, how do I calculate return on investment? These are our RO series. These are the standard series for softened water. That's 57 to 80% recovery and usually a typical conductivity in the permeate of less than 20 microsiemens per centimeter. We have here several unit ranges, and what is important for you is that this one has been redeveloped. The UOD, it used to be UOD ND, and this used to be available with and without variable speed drive. And since we have really always a return on investment for these flow rates, we produce this only with variable speed drive anymore. We have here our special units, let's say, for softened water. These are the KR units. That has the KR unit has a higher water recovery. This also definitely something that's very useful. We did a webinar on this as well because the water cost makes up an even higher part of the total operation cost or the total ownership cost than electricity. But you'll see that in the later examples. We have the permeate staged units and we have the ultra pure water units, that's RO plus EDI. For the KR and the ultra pure water units, we also offer units from this year on with variable speed drive only because it makes a lot of sense for these flow rates. You will always have a pretty quick return on investment. And here finally, we have the last part. These are the hard water units, let's say, the ones that run with anti-scale. This is our UODAS series. These two, the UODFO and the UODAS, have been generally revised this year completely. So we also took out, let's say, the need to use pressurized air for the valves. The anti-scalent units are now available from 450 liters per hour on. Before it was 2,500, I think, 1,650. So we also offer quite small anti-scalent units. And we have the brackish water units. Now I just show you the ones that are marked here with yellow or orange. These are the ones that are available with variable speed drive only from now on. Just a quick explanation of some details. So for these smaller units here, the 600 to 2000 liters per hour, we still offer both versions because there are some clients that are very, very price sensitive and it's hard to convince them. And as a tendency, the let's say payback time for these are also slightly longer than for the larger units. So here we offer still both options, but I show you also a calculation example for 1.5 cubic meters per hour where it's definitely worth it to use a variable speed drive. These larger ones, they are all available with variable speed drive now. Some small exceptions. Here, the permeate staged series, we have small units, the 200 and 400 liters per hour. These are not centrifugal pumps, so these are not available with variable speed drive. And the same goes for the two smallest ultra pure water units, 150 and 250 liters per hour. Those are also different pump drive. So two smallest units from these series are not equipped with variable speed drive. All the others are. Okay, now let's go to calculating the savings, the important part. First of all, we need to just have a look at our basis of calculation. We want to compare the energy consumption of units with variable speed drive and without, okay? We compare always the power that we take from the electrical grid, P1. So we consider the losses of the variable speed drive already. Then we'll have data in the tool for the series UOD and UODAS. If you need data for other series or a calculation for other series, drop us a line or contact us and we'll have a look. And now something very important, load cases. So it's very hard to say exactly, to have all the data from the client and to know exactly how the unit is going to run in the field, under which conditions, to know what energy saving you can achieve. You would need a lot of data points for that. You would need all the data from the client. It's usually not possible. So we have thought about a solution, and that's we define load cases. So we have load case 1, 2, and 3. That's a minimum, typical, and maximum deviation from the design point. The more you deviate from the design point, the higher your potential saving with a variable speed drive. I'll show you the different load cases. This is our design point. So we design our units for 1000 milligram per liter TDS in the feed. This used to be a limit value for drinking water. That's why we have taken that one. And that means you always have the safety that you know, even if you don't have a water analysis, the unit is going to run with drinking water, definitely. We usually use a feed water temperature of 15 degrees Celsius, and we need a feed pressure of at least 2 bar. Now, when our units are in the field, how they're running, that's more or less, let's say, a Gauss curve, a normal distribution. If we say the design point is here, where my dot is, then we have some units, maybe around 15% approximately, that run with a minimum deviation. We have a lot of units here, like 70% maybe, that run with a typical deviation. And here's some that are very far away from the design point, maximum deviation. We have defined minimum deviation as maybe TDS of 800 milligram per liter, still quite a lot, you know. Feed temperature still 15 degrees, and feed pressure just slightly higher than what we have as minimum. Then we have a typical deviation. That's how most of the units are running, more or less. It's 500 milligrams per liter TDS. That's very typical what you find in a wide variety of drinking water supplies. We have 18 degrees Celsius, which you can reach really easily. And we have 3 bar feed pressure, also not too much. And then we have defined maximum deviation, 300 milligrams per liter TDS. That's what we have, for example, here in our test field in Freiberg with a drinking water supply. 20 degrees Celsius. In summer, we are far higher than that actually here. And feed pressure of 4 bar. So this is what we have defined for the load cases. You will see these are all really normal values. You will see a lot of units running in the field. You might have units that run even with more than the max deviation. That will happen. But we have wanted to really, let's say, cover most of the units. Now you could say, hey, don't we have a deviation to the other side? Theoretically, yes. Practically, the plant is not exactly going to run with a deviation to the other side. So if we go here in that direction and we say the TDS is higher, you need a different unit because this is the maximum, right? Then you need a brackish water unit. If the feed temperature is lower than 15, you will not get the permeate value or the permeate flow rate that the unit has because you need a higher pressure. In that case, it's also good to have a variable speed drive because you can adjust the pressure. But it's something that we will not look at right now with a lower temperature. And with a lower feed pressure than 2 bar, obviously that's not going to work. So we can always go in one direction. So with the TDS down, with the temperature up, and with the feed pressure up. And this is also what you see in reality normally. Now we come to the calculator. We have the savings calculator here. You have first a part where you put in the project data. You have here a drop-down field where you can choose your type of unit, which unit size you have. Is it a UOD, UODAS? And then you see here what is the permeate production, feed water, concentrate flow. You can also fill in the yield, 70%, 80%, whatever you choose, okay? It's not that relevant for the energy consumption really, but it's relevant for the water consumption, and we have included the water consumption in the unit or in the calculation so that you have a full picture. You choose the lifespan of the unit. We would expect 15 to 20 years. You choose your operation time in days and hours, and you fill in the water and wastewater cost and the energy cost. €2 here is pretty typical. Here we have 40 cents. You can adjust that however you want. You can leave out the water cost if you don't know it and don't want to look at it. No problem at all, okay? So this is not protected also. You can choose what you want. Be careful not to make any mistakes when you change it, but we wanted to give you a maximum degree of freedom so that you can adjust it to your needs. We also give you automatically here the project cost. This is a list price of the units as it is in our catalog. if you have a different price that you actually give your client, lower, higher, whatever, depends on the project, you can override here. So you can just write in something. Just be aware that then the link to the data is lost. So just keep a backup version of your Excel sheet, okay? And we also have a look at, okay, this is the unit price that we have right now. This is what we think the variable speed drive equivalent is approximately from our experience with our units. So this would be theoretically the price without variable speed drive. You know that we don't offer this type of unit anymore, but it gives you a comparison with units of somebody else. Okay. Now, with all this input, we can calculate. And when we calculate, we have here the different load cases. So we calculate first pump pressure and power demand, then the yearly operation cost, and then later we come to the next calculations. You will see here that you have a calculation without variable speed drive. Okay, that's the base case. This is the calculation with variable speed drive at the design point. So both of these are at the design point. And this is with a variable speed drive with a min deviation, typical deviation, and max deviation. You have the design, the calculation without variable speed drive only at the design point, because remember, when you use a throttle valve, you always come back to the same pressure and flow combination. The pump cannot run anywhere else. So you cannot reduce your energy consumption if your load cases differ. But with a pump with a variable speed drive, you can. You see here, this is the pressure you need with a not regulated pump. This is with variable speed drive. It's already a bit lower because you remember you have always a certain safety margin in the pump, a bit more pressure than you need, and you can reduce it already with a variable speed drive. And then you see that here you need other pressures for the different load cases, which are lower than the pressure of the pump without VSD. And of course, the power demand of the pump is proportional to the pressure that you need. So we have looked for all this data. All this data is in a second sheet in our tool, and it just pulls the data depending on which unit you choose. You see here the connected load as well. Here's a case where the connected load is lower than the power demand. Typically, the power demand is lower than the connected load. We have included that just for information. Now, with the power demand given here, the costs are calculated. You see here the maintenance cost. This is estimated as a percentage of the investment. It's not higher for the pump, for the unit with VSD, because we actually have a lower maintenance need in general because of the soft start. The water and wastewater costs are the same for all the load cases. That makes sense because we haven't done anything about the water. And the energy costs differ. All right. Now, we had a look at the yearly operation cost. We also have a life cycle cost. The life cycle cost includes the investment, maintenance, water, wastewater, energy over the lifetime of the unit, the lifetime that you fill in the beginning. And we show you the energy saving over the entire lifespan. So we give the additional cost of the FU unit, VSD unit. We give the savings, the energy savings of the lifetime, and we give the savings as percentage of the total invest, so percentage of the unit. Okay. And finally, we'll come to the thing which maybe is the most important for the client in the beginning, and that's the amortization or payback period. Here we show you again the different load cases, so you can choose which load case you want to look at. Maybe you know already that the client is quite far away, you need to use maximum deviation. Maybe you know you have less deviation. Typically, we recommend that you compare this column, so without variable speed drive, with variable speed drive and typical deviation, because this is what we usually see out in the field. You see here, you don't need to look so closely at the absolute numbers. What is important for you is the green marking. You have here the investment cost, first of all. Then you have the cost in the first month, second, and so on, up to month 24. I think in the tool, it's actually up to 30. So 2.5 years. And it just gets added up. So you have a total cost, okay? And you'll see how this is at first the cheaper version, and then at some point you get to the point where you have actually a lower cost here and a higher cost here. And this is where the payback period for the additional variable speed drive cost is reached, okay? Where your total cost of ownership is lower with a VSD than without. And from then on, you have a lot more investment here, or a lot more, let's say, money that you put into this unit than into this unit. And you see already, here we are at the end of 292,000, 282,000, 80, 77, 75. So the further we are away with the load case from the design, the more savings we have. All these calculations are, as I said, not protected, can be adjusted, are optimized also for printout on A4 or on PDF. So you can add them to your quote, show the client what he can expect, and it's good to convince the client or to calculate also different options for a larger project. What we have also done is to show the life cycle cost as a cake diagram. This is, for example, standard RO unit. This is without variable speed drive. What is here really interesting, look at this total cost. This is for 15 years lifespan, which is very typical. Usually it's more like 20 years. This is your original investment. It's 5% of the total cost. And it's really important because I find it always surprising, was surprising for me too when I first calculated that such a small part of the total cost. And we have not assumed any exaggerated water, wastewater, energy costs. So it's really important to show the client this is one thing that you're looking at, but from the unit you buy or the equipment of the unit, the proportion of this cost follows. It's a really, really big influence what unit you choose on the final cost for the client. Look at this and look at the next slide. Okay, you see that? This is the energy cost, yellow. Oh, sorry, you see how it changes? This is the unit with the variable speed drive. You have a lot lower energy cost. You have a lot lower total cost. This total cost was 875,000. This one is 694,000. So you see, that's really, really a big difference. Now I show you two more examples, and you can check all this for yourself with a calculator. This is a life cycle cost example with a small flow rate. I talked about that. This 1.5 cubic meters per hour. And even for this unit, you see that after 19 months, that's less than 2 years, and in industry, a payback period of 2 years is considered good. You have already the payback for the additional investment for the variable speed drive. This is with 40 cents per kilowatt hour, which is also not an uncommon price right now. And in the total lifetime, you will save 180% of your invest. So this here, with the in electricity cost with the equipment with a variable speed drive. We'll have a look at a large unit now. Here I have assumed a lower electricity cost, 20 cents per kilowatt hour. I do not think you will have many clients who have anything lower than this. And you can see that for larger units, even with this relatively low price, you have a payback period of just 5 months. That's really little. And you see how the total cost varies from year to year. Okay, you can see here 137,000 to 240,000. It's a big difference. You also see something here, and that is, look at the water cost. Water cost is a big factor as well. You can think about our KR units that have a higher recovery. That's also a great way to minimize water cost. The tool can be used to have a look at water cost as well, so you can adjust that as well and see what happens when you adjust the permeate recovery. Okay, to recap everything, we're almost finished. I want to show you in general what are the biggest advantages. First of all, what we talked a lot about is energy saving. It's obvious. You save 30 to 50%, up to 65, 70 in some cases, depending on your operating conditions. So 30 is really practically always, and in most of the cases, you are at 50%. Apart from the energy saving, you also increase the lifespan of the unit. So it's a big advantage not to have these water hammers when you start up. It's a big advantage to be sure to always run at the correct operation point. Don't need to readjust. You have a really silently running unit. That's a great advantage as well. And finally is the sustainability. So this unit is going to run not only now, this unit is still going to run in 20 years. We're replacing right now units that are 20 years old. If you think about the electricity cost now, you know that in 20 years it's going to be quite a bit higher. So it's important to consider for the environment, but also for the client, that it's a good idea to invest now this really small amount to have a unit that will save money for years to come. We have formulated this, what I've told you just now, the energy saving, lifespan of the unit, and the convenience and the sustainability, so that you can also use that, for your sales talk. We offer you also a small brochure, like a one-pager, let's say, to show the advantages of the unit. And we offer you the Excel tool that you can adjust. So we'll send you the handout plus the Excel tool plus this brochure, and you can use that to really show the advantages of this of the variable speed drive. And of course, if you have any more questions, either directly now or later about a certain project, we're always there to help you. So I hope I could show you the really significant advantages of this technology. I think you will understand why we want to equip all our units with a variable speed drive. And I hope this is a help for you when you show the client the advantages. And I say thanks for your time. If there are no more questions.